Welcome back. We are in chapter 3.9. And the title of this chapter is Linear Approximation and the Derivative. So we've seen before that when we zoom in on the graph of a differentiable function, it looks like a straight line. And remember, differentiable means you can take a derivative of it. That was one of our vocab words from before. Now, technically, it isn't a straight line. But it's close enough that we can't tell just, oops, sorry about that. We can't tell just by visual inspection. And that straight line we think we see when we zoom in on the graph f of x at x equals a. So we're being a little more specific, right? We're zooming in on the graph of f of x. We're zooming in at the point x equals a. So that straight line that we think we see when we zoom in has slope, sorry about that, has slope equal to f prime of a. So the derivative is the slope. So the equation of that straight line is y equals f of a plus f prime of a times x minus a. And the fact that the graph looks like a line means that y is a good approximation for f of x. If we zoomed in and it didn't look like a straight line, then we shouldn't be using a straight line to estimate it, but If we zoom in, it looks like a straight line, then this is probably a good approximation. So that brings us to the tangent line approximation. Suppose f is differentiable at a. Then, for values of x near a, the tangent line approximation to f of x is f of x is approximately f of a plus f prime of a times x minus a. So that's our line from before. And the expression f of a plus f prime of a times x minus a, often it gets a special name. Often it is called the local linearization of f near x equals a. And just a note, we are thinking of f of a, or sorry, we are thinking of a we are thinking of a as fixed. So f of a and f prime of a are constant. And we also get to define the error in our approximation. So the error, which we'll say that's e of x, in the approximation sorry, my dog just kicked my papers everywhere. The error in the approximation is defined by e of x is equal to f of x minus f of a minus f prime of a times x minus a. So we see here that that was our approximation that we were subtracting off. And your book has a very nice visualization of this. So I'm not going to attempt to draw it on an iPad, so I'm just going to make a note that there is a nice visualization of this. In your book. So I recommend you go check that out. That can kind of help you put the pieces together and see what's going on. We are going to move into an example. So in our example, we want to know what is the tangent line approximation for f of x equal to cosine of x near x equals pi over 2. So what is the tangent line approximation for the function cosine of x when x is pi over 2? Well, our definition from earlier tells us that that's going to be approximately f of pi over 2 plus f prime of pi over 2 times x minus pi over 2. Great, so we've got it written in terms of f's. Now we actually need to go find what are these values. So first up, sorry about that. First up, I'll say I'm interested in the derivative with respect to x of f of x, which is the derivative of sine of x, which is, sorry. Okay, so I'm interested in the derivative of my function. My function is cosine of x, and the derivative of cosine of x is negative sine of x. So now I've got my function, I've got its derivative, I've got x, I can start putting the pieces together. So f of pi over 2 is equal to cosine of pi over 2, which is 0. F prime of pi over 2 is equal to negative sine of pi over 2, which is equal to negative 1. So then f of x is approximately 0 plus negative 1 times x minus pi over 2. So we get that f of x is approximately pi over 2 minus x. So that is the function that we would think we see if we zoomed in on the function cosine of x near x equal to pi over 2. That's one type of question you might see in this chapter. We'll do an example that shows you another type of question. So in this example, we want to know what is the local linearization of the square root of 3x plus 7 near x equal to 2. So local linearization was another way to say the right-hand side of that equation. So again, we're basically still just looking for this approximation, which in this case is f of 2 plus f prime of 2 times x minus 2. And we'll find f prime of x. This is going to be a chain rule situation. So f prime of x is 1/2 times 3x plus 7 to the negative 1/2 times 3. As we move on and get more used to these things, I'm going to spend a little bit less time explaining in detail how to do things like the product rule and the chain rule during the notes. But if you have questions about it, I am more than happy to talk about it in office hours. So just sign up for office hours and let me know. So I can rewrite this as 2 times the square root of 3x plus 7. All of that in my denominator. So now I've got my function, I've got my derivative, and I've got the x value, so I can fill in the pieces. F of 2, that is the square root of 3 times 2 plus 7, or the square root of 13. F prime of 2 is 3 over 2 times the square root of 3 times 2 plus 7. So that gives me 3 over 2 times the square root of 13, but we don't like having square roots in the denominator, so I'm going to get rid of that. The way I do it is I multiply both the top and the bottom by the square root of 13. So I end up with 3 times the square root of 13 over 26. Putting that all together, f of x is approximately the square root of 13 plus 3 times the square root of 13 over 26 times x minus 2. And since we wanted the local linearization, technically, I will stop making the screen jump around next time, I promise. Technically, since we're just after the local linearization, we don't need the f of x is approximate to, we can just say the right-hand side of that equation. So that is the end of